before we get started on today's lesson, are there any questions on any of the assignments so far? So we're good with all the assignments thus far? Yes, with the two we've done. What we're starting off today is the properties of exponents. And most of these properties y'all have worked with before, and we've done before. Because our first main property is powers, product of powers. If we have like bases, we add the exponents. Use black and green. A to the m times a to the n will be a to the m plus n. Our next one is power of a power. Whenever we have a power of a power, we multiply the exponents together. Power of a product. So if we have two things multiplied together to the same exponent, each term gets that exponent. And that's a little bit different than addition, because if it was going to be a plus b to the m, we have to multiply it by itself. Our next property that we have is negative exponents. Really just says a to the negative n is 1 over a to the n. And we can go the other direction too, in that if the exponent is negative in the denominator, we can move it to the numerator. And normally everyone's favorite is the zero exponent property. Which anything to the zero exponent is 1. Anything to the 0 power is 1, besides 0. Quotient of powers. Our quotient of power property states if we have two like bases being divided, we subtract the exponents, and the exponent in the numerator always goes first. And then the last one, power of a quotient. A divided by b to the n is the same as a to the n divided by b to the n. And really, with all of these here, we are going to be manipulating these to get the answers to work out better for us, especially with these rational exponents. And most all these properties we've seen before. And the reason we're going to be utilizing these is to get the expression in simplest form. Now there's three main things we need to be able to say that it's in simplest form. No radicands have perfect nth powers as factors other than 1. Essentially, we can't have something like, erase that. I can't leave it as a square root of 4. If we can reduce whatever's inside the radical, we need to. So the square root of 4 we can't leave as the square root of 4, or the cubed root of 8. If there's a power or a number that can be pulled out, it has to be pulled out for it to be considered in simplest form. Another way we can say this is say 2 to the 2/4. 2/4 is not in simplest form. because it can be reduced. If we can reduce it, we need to reduce it. Second main thing. No radicands can contain fractions. I can't have a fraction inside of the radical. And we call what's inside a radical the radicand. And the last one, no radicals can appear in the denominator of a fraction. We can't have radicals in the bottom of a fraction. And the main reason for this here is we don't want to have an irrational number in the bottom of a fraction, something we're dividing by. And that's really the only logical reasoning for that. Otherwise, it's not too big of an issue. And the third one is normally referred to as rationalizing the denominator. Any questions on this so far? We ready for some examples to see how this works? Use the property of rational exponents to simplify each expression. Now, luckily for these here, I'm not going to have you rewrite it as a radical. We'll leave it as fractional exponents. Now, we look at this first one here. We have 7 to the 1/4 times 7 to the 1/2. If the bases are the same, both 7, and they're being multiplied together, we're talking about our product of powers. We're going to add the exponents. So we're really saying that we have 7 to the 1/4 plus 1/2. And really at this point here, we could go through the whole process of the fact that, well, to get the two fractions to be able to add together, we've got to get the bases to be the same. And, well, we can do 1/4 plus 1/2 in a calculator, and it would tell us what that is. Because again, at this point, we're not really using or focused on how to add two fractions together. We're more focused on the properties of powers. So adding those together is fine. And this here might be the final answer. We just need to check a few things. One, is our fractional exponent in lowest terms? Yes, we can't simplify it any farther than 3/4. There's no common number on top and bottom. Well, 7 is a whole number, so we don't have to worry about fractional numbers. There's not a fraction that's connected to it, and there's no radicals in the denominator. Another way that we can see a radical is, well, if it has a fractional exponent. So we can't have a denominator with a fractional exponent. So, since it checks out of all those there, that is the final answer. Let's look at the next one. 6 to the 1/2 times 4 to the 1/3. Whenever we look at these here, well, 6 and 4 is what I would look at first. Are they the same? Are they have like bases inside there? Are 6 and 4 the same? No. Another way we can see or look at this here is there any way that I could rewrite 6 as a number to a power? that would be the same as 4. Well, we could rewrite 4 as 2 squared, but 6 is not able to do that. I can't write 2 to a nice whole number power to get 6 or any other number. So we can leave those alone for now. But we do have power of a quotient. Because of the 2 on the outside means that I'm going to multiply or apply it to both of these here. We're multiplying the 2 by both of our fractional exponents. So for the 6, we're going to have 6 to the 1/2 times 2 times 4 to the 1/3 times 2. Any questions on this so far? Now we can multiply these here together. And if we multiply these together, well, 1/2 times 2 for our 6 is going to be 2/2 times 4 to the 2/3. Okay. Thought so. Just wanted to make sure. Well, erase it there. Didn't erase the whole thing. Okay, apparently I'm going to keep erasing. 4 to the 2/3. So this here could be our final answer because we know 4 and 6, we really can't multiply them together at this point unless we actually apply those exponents, those fractional exponents. But is there anything else we could reduce? The 2/2, which would just make this times 4 to the 2/3. The 2/3 is in as simplest form as it gets, and we can actually leave it here. That's why I was looking at the book, because realistically, as we said already, 4 can be written as 2 squared, but we're going to leave it alone. The only reason I would rewrite it as 2 squared is if there's a chance that it would simplify down. If there's a chance that rewriting this as a square could somehow simplify that fraction. Does that make sense? Because if this had been 3/2, then rewriting it as 4 squared, kind of like what we saw yesterday, would simplify that fraction down, and we can get it in a simpler form. But here, all that would do is change it from 3/2 to 4, from 2/3 to 4/3. It's not making it any simpler. That's about as far as it goes. Any questions on this here? All right. Let's look at the last one, C. So we have 4 to the 5th times 3 to the 5th to the -1/5. So as we've seen so far, we're using these properties of powers. Which property do we want to use first? Our power of a quotient, or power of a product, applying the -1/5 into both these here. Yes, we can do that first. So we'll have 4 to the 5 times -1/5 times 3 to the 5th times -1/5. Now at this point here, we can go on and multiply those exponents. So 5 times -1/5 would be -1. Because 5 times 1/5 is going to be 1. And since one of them is negative, it would stay -1. Times 3 to the -1. Now, I didn't include it. I've probably said this 2 or 3 years in a row. I need to go back and include it. We can't have negative exponents. That's just one of the basic properties. So to make these exponents positive, we'd have to move it from the numerator to the denominator. from the top to the bottom or bottom to the top. So if I move the 4 down, it becomes 4 to the first, positive first power. And if we move the 3 down, it becomes 3 to the positive first power. Is there anything else we can do? Can we do 4 times 3? Do they have any exponents besides 1? No. So that works out to be 1/12. So this one here, unlike the last two, we could have actually plugged this into a calculator and gotten an answer. Because all the exponents, our rational exponents, did simplify out, and it came out as a nice number. But the previous two would not have been so, because 4 to the 2/3 is not a whole number. 7 to the 3/4 is not a whole number. We can't just have that in the calculator and work out. And most likely, we'll eventually get to some, and on the ACT, they'll throw some in that have variables instead of numbers, which most of the calculators allowed on the ACT won't do. Any other questions on these here? Okay, still using properties of exponents to solve these. Now the first one we have, our next one that we have is 5 divided by 5 to the 1/3. Are the bases the same? Because we have 5 and 5. Because the bases are just whatever number or variable or expression that we have to an exponent. So in the numerator, we actually have 5 to the first, and in the denominator, we have 5 to the 1/3. So using our quotient of powers, if the bases are the same, we can subtract the exponent. So 1 minus 1/3. And 1 minus 1/3 is 2/3. And we've done this before, especially in the last chapter. When we had x over x squared, we subtracted the exponents. If it's bigger on bottom, it stays on bottom. If it's bigger on top, it stays on top. And it's using this property here, because if the number is bigger on bottom, it's going to give us a negative exponent in the numerator, which means it's actually got to go back to the bottom. If the number is bigger on top, if we're subtracting a smaller number from a bigger number, it should stay positive, so it'll just stay in the numerator. Now looking at this here, well, 2/3 is as simplified as we get. And there's nothing else going on here, so 5 to the 2/3 is our final answer. And again, we can't take 2/3 of 5, 5's prime, so it would give us a decimal if we tried to plug this into the calculator. Any questions on this here? Okay. We good with everything so far? Yes? Let's look at the next one here. This one here I find interesting because it's a little bit easier than what it might look like. Now looking at this here, we can tell that 42 and 6 are not like bases. They don't have anything in common. But 42 and 6 are both put to the same power, yes? They're both to the 1/3. And what we really can use first in manipulating this is power of a quotient. Because the power of a quotient property states that a divided by b to the n is equal to a to the n divided by b to the n. And we've used the power of a product before already because we applied the power to it. Well, here I could use it with the 2, but we could do something else. Instead of applying it to both, what we can do is what? We can remove it. I could remove the 1/3, and then we would still have the square on the outside, because I could pull that 1/3 away. Which I was like, why does that matter? Because what does that leave us inside? 42 divided by 6, yes? Is 42 divisible by 6? So that tells us that we have 7 to the 1/3 squared. This is why these are helpful. Because if I can start manipulating them so that I have something like this here where they do divide well, and I don't have to worry about that 1/3 and 2, we can do that and make it simpler. Well, now we're going to multiply the powers together. The 7 is to the first, which really isn't a huge deal, because 1 times 1/3 is just 1/3 times 2 is, and that would be it. So we got the radicals away from the denominator, our 6. Our exponent is in simplest form, as simple as we can get it. And that's as far as it goes. Questions on this here? So most of this here isn't really doing a whole lot. It's just really manipulating these equations so that they are in simplest form. Well, first one here, 2 to the 3/4 times 2 to the 1/2. We can try and see what we get. Since the bases are the same, we can add the exponents together. When we multiply like bases, we add the exponents. So we'll be seeing what 3/4 plus 1/2 is. 5/4. And I believe that is our final answer, because the only other way that we could rewrite it is splitting that apart, which would be our 2 times 2 to the 1/4, which in my opinion isn't making it any simpler, it's just changing how it looks. Yep, that's it. Does that make sense? So with our fractional exponents, or fractions, if we're going to be able to add 2 fractions together, the bases have to be the, what do I need to multiply 2 by to get it to be 4? Multiply top and bottom. So 3/4 plus 2/4. 3 and 2 is 5. Yep. And for the most part, these here, especially with that addition, subtraction of fractional fractions, we could do that in a calculator. So the yellow calculator, 1/4 or 3/4 plus 1/2, enter, it'll do it for you. But unfortunately, we can't type the whole thing in 2 to the 3/4 plus 1/2 because it doesn't give us a whole number. Let's look at the next one. 3 divided by 3 to the 1/4. Now here, because the bases are the same, we can subtract the exponents. So this would be 3 to the 1 minus 1/4. Which would be 3 to the 3/4. And that'd be it. Because we don't have any fractional exponents in the denominator, they're only in the numerator, we can't simplify any further than this here, so we're good. Any questions on this here? So really, having improper fractions, 5/4 is fine. If it was 10/8, then we do need to pull it down. Okay. So what can we do with number 3? So we'll use our quotient quotient of powers property, or power of a quotient, where we have a quotient to a power, and we can pull that 1/2 back out. I can put them on my desk. And what that would leave us with inside is 20 divided by 5. Well, 20 divided by 5 is 4 to the 1/2 to the 3rd. Now, this one here will actually give us a whole number. Because what we're looking at here is 4 to the 1/2 to the 3rd, yes? We know that 1/2 is the same as what radical? Our square root, yes? So we're really saying the square root of 4, which is 2. Another way we could see this is saying that 4 is our 2 squared to the 1/2 to the 3rd. This is what I was referring to earlier. This is one of the cases where it's nice to rewrite it this way because it's actually making it simpler. Because our 2 times 1/2 would become 1, which would give us 2 to the 3rd, which is 8. So this here is one of the few that we could have actually typed into the calculator and got the answer. Yeah, it would have given us 8. Now, if it hadn't been 1/2 as the or one of our exponential powers or our fractional exponents, it wouldn't have worked out this way. It's mainly that base of 2. So really with 4, any even base, we would have probably needed to write it that way because then it would simplify, because that 2 would simplify. So here we get 8. Questions on this here? So the last one on this page we have here. 5 to the 1/3 times 7 to the 1/4 to the 3rd. So our product of a power, we're going to multiply the exponents by 3. So we'll have 5 to the 1/3 times 3 times 7 to the 1/4 times 3. Well, 5 1/3 is just going to be 5 because 3 times 1/3 is 1 times 7 to the 3/4. And that's as far as it goes. We don't have any radicals in the denominator yet, so we don't have to worry about it. All of our exponents are positive, and we can't reduce any of the exponents. We don't have a common term on top and bottom. Having a bigger number in the numerator of our rational exponent is fine. Any questions on this here? Any questions over anything we've done so far? So we still have 15 minutes left of class. I have more of these that we can do. Or, yes. Simplify 25 to the negative 1/2. Now, to make that exponent positive, we have to move it from the numerator to the denominator. Now, what do we know about 25? It is an odd number. It is also one of our perfect squares. Well, okay, that's kind of helpful to know. But if we look at the exponent as 1/2. So, okay, most likely I'll need to rewrite it as 5 squared to the 1/2. And really looking at those there, a lot of them just making sure checking our powers. So if it's an odd power cubic, like 8, can be rewritten as 2 to the third. Can that 3 in the denominator of our rational expression simplify in any way? Or with the radical, can we reduce it? Can we pull it down? Then we do. A lot of, if we can rewrite it as a square, is the denominator of the fraction an even number? If it is, okay, we'll need to do that to get it to simplify. And well, 2 times 1/2 is 1, which actually just gives us 1/5. Point 2. You're good? Any other questions on this here? Let's look at this last one here. And then I'll give you all the rest of the time to work on the assignment. The assignment is, I think, 8 problems. Okay, now looking at this one here, nice if I didn't put that so close, because what we can do is we can rewrite this as 12/3 to the 1/6 to the 4th. Or the 1/6 to the 4th. Now it looks like that fractional exponent would reduce with the power of 2 if we rewrote it as 2 squared, yes? But we're also multiplying the 1/6 by what? 4. So I'm more focused, because again, there's different parts when we look at this here. Because if I do this multiplication, what would we get? 2/3, okay. So here we'd have 4 to the 4/6, which would be 4 to the, will that 2, that when we rewrite the 4, actually simplify anything? Well, not anymore, right? Because the 4 on the outside actually simplified that from 1/6 to 2/3. So even if I rewrote 4 now as 2 squared, that square in this 3 won't simplify anymore. So we can leave it as 4 to the 2/3. So this here, a lot of this here is a little more fluid than some of the other concepts that we've done. Because a lot of the concept that we've done is this is the way it works, this is how it always works, this is it. This is kind of more closer to our factoring, which is based off the setup. And that's all it is saying, okay, how is it going to simplify? What's going to be the easiest, well, not easiest, the best way to simplify it? And working it one problem at a time. And manipulating the numbers as best we can to get it to work better for us. Any other questions on this here? Because I did put more in here, but that's all we're doing for today.